The scenario is what we call, or what the GMAT calls, GMAT questions call, the rectangular coordinate system. Some questions even mention that in a rectangular coordinate system, or they may say in the XY plane, or they may say in the XY coordinate system. Yeah. Either of the three, which is what you see on the screen, right? A virtual plane, which is simply a way of representing positions over, a flat plane. And in order to do so, you have two axes, right? Two axes, horizontal and vertical, by means of which you can represent the position of points on this plane. Each point is represented as, a pair of real numbers. The first one, the leftmost, representing a horizontal position. Yeah, that's a position mark over the horizontal axis, and the rightmost represents the vertical position. I believe everyone is acquainted with this representation system, right? What it's likely you might not remember is the way this virtual plane, the XY plane, is divided. The two axes are actually two infinite straight lines which cross each other, forming a 90-degree angle, or a right angle, or like a perfect cross. Yeah, you name it. And there are four infinite divisions that they are called quadrants, right? And the first one is always the rightmost upper division, this, and then they are numbered or sequenced counterclockwise. All right, so you have the second to the left, the uppermost, then below you have the third, and then finally the fourth, right? So, and based on a convention or a universal agreement on how to label the positions, the intersection point of the axis is considered to be the reference point for all positions, and that's called the origin, right, of coordinates. Consider that any positions to the right of the origin, horizontally speaking, are considered positive. Pretty much like in a normal number line, right? In the representation of a number line, any positions to the left of 0 are considered negative. And in the vertical axis, any positions above the origin are considered positive. Any positions below the origin are considered negative. So that convention determines what the signs of the numbers called coordinates to represent the positions of a point on the plane. The signs are predetermined. You can see that the first quadrant, both coordinates must be positive. In the second quadrant, the horizontal coordinate is negative and the vertical coordinate is positive, and so on, you can see. We'd better, be aware on this convention and memorize, the signs. You could even wonder, some questions actually target the fact that you remember that convention, that way of defining the sense and the sign of positions on the plane. So basic questions may relate to the most basic objects on this plane, which are basically points, right? But then, after points are defined and understood, the next object you might deal with in GMAT questions could be line segments. But if a line segment is a portion of a line, a straight line between 2 points, how do you define a line? Yeah, that's been, even a philosophical question, right, for many centuries. The idea is that in the GMAT, we deal with something called Euclidean geometry. Geometry follow the principles of this variety of geometry agreed on a simple premise. They call it an axiom. that a straight line, is the shortest path between any two given points. Yeah, that works for GMAT geometry, GMAT coordinate geometry. It doesn't work in other geometry systems, but here it will do. So if a straight line or a line segment is the shortest path between 2 points, but how do we represent that analytically? How do we define a rule, uh, which um, the coordinates of any points belonging to the same straight line would have to satisfy? Here is where algebra, uh, comes to help. Because if a straight line is an infinite set of points that constitute the shortest path between 2 points, but if we don't define such 2 points, how do we define otherwise a straight line? Well, basically, a straight line would be defined as the set of points whose coordinates, x and y, uh, belong each, to this set, r squared, which is, x belongs to real numbers and y belongs to real numbers. Yeah, each of these is a pair, or each of these is a real number, right? So it might be any value. And such that the coordinates, the values of these coordinates of points belonging to a same line, simply have to satisfy a common linear equation with two variables, such as this. Like this, if you will, or perhaps like this. Many ways to actually represent a linear equation, a general linear equation with two variables, where x and y are real variables, and a, b, and c are simply constant values, also real numbers. So that's it. That's a definition of a straight line. Analytically, a point on a straight line is such if the coordinates of that point satisfy a given linear equation with two variables. So we can see how then the definition of a straight line in GMAT questions is related to such equations, right? Of course, the equations can be presented in a number of manners. What happens particularly when the equation, a linear equation with two variables that defines a straight line on a plane, is modified such that we isolate the variable y. So it would look like this, right? Y equals a constant value multiplied by x plus another constant value. So let's call these constant values m, the coefficient of variable x, and b, the independent constant. So when the equation that defines a straight line is expressed like this, in this second form, that's the geometry form that's called, and it's of particular interest for GMAT candidates because the constant values m and b, they actually acquire more serious meaning, from a geometric standpoint. How is that? Well, for once, this value, this constant here, represents the precise position over the vertical axis where the line represented by this equation crosses that axis, the vertical axis. So that position, that, let's say, vertical coordinate, because this point would have the following coordinates: being located precisely over the vertical axis, its horizontal position will have to be 0, but the vertical position will be that constant b. So it has a geometric meaning, right? What about m? Well, probably you remember, probably you don't. M is a number that receives this name, the slope of a line. And it is related somehow with, this, the angle the straight line forms with a horizontal axis. Okay, it has a relationship. So this number tells you um, information about the orientation of the line regarding the horizontal axis, and also regarding the vertical axis, of course. And it also tells you how steep or how flat the orientation of the line appears to be in relationship to, for example, the horizontal axis. The constant b has also its own name, the y-intercept. Yeah, because it's precisely the position over the vertical axis or the y-axis where the line intercepts, the axis. And therefore, there is also something called the x-intercept, which is, the horizontal position on the horizontal axis where the line crosses that horizontal axis. So here the idea is that these two values, which are two real numbers, can be obtained by equating one of the variables in the equation of the line to zero and isolating the other. That happens when you substitute x for zero, then you have y equals b. So that's the value of the y-intercept. And if you substitute y for zero and isolate x, you get this expression, right? The x-intercept, this value is actually this. So this point here, the point where a line crosses the horizontal axis, has these coordinates. Always. Okay, so that's the importance of constants m and b, which are defined when you change the form of the equation of a line into this, which means simply isolating variable y on the left side. So some questions may require that you, for example, work with some points which are set to be part of a common line, and you need to identify the equation of the line. So what you need in order to define this equation, you can see either in this form or in this form, particularly the geometry form, you see that the equation that defines a line would be fully defined if you just knew the values of m and b, right? That's all you need, and you have a complete equation. In order to define these two constants, you can start from knowing the coordinates of 2 points that belong to that line. You want to define or find out its equation, or knowing the coordinates of 1 point belonging to that line and the value of the slope, that is, of the constant m. So, and saying that a point belongs to a line, is based on this definition, this algebraic definition. Basically, how do you test whether a point belongs to a line? You just substitute the coordinates of such point in the equation of the line, and if the coordinates of the point satisfy the equation or make the equation true, then obviously that point belongs to the line. If it doesn't, if the equation doesn't turn out true, a true equality, then it means that that point doesn't make part of that line. So that's basically how you test points versus a given line. All right, so let's see some example here. You are given, for example, this linear equation with two variables. Yeah, nothing fancy about it. That's a simple equation, right? This represents a given infinite straight line on the xy plane. How do we find the representation of that line graphically on the plane? Well, one way is simply reasoning like this. If you have two different points on a plane, there is only a single straight line that connects those two different points. not more than one line. Just a single line will connect two given points on a plane. So basically, if that's true, that's an axiom, right? Then finding two points that belong to the line and connecting graphically those 2 points, that would do. That would suffice to represent a straight line based on a given equation. So what if those 2 points that we can graph over the xy plane and then connect them, to define the line, are basically the 2 points where the line intersects the two axes, the horizontal and vertical axis. So if you want to find the x-intercept, the position where the line crosses the horizontal axis, you just need to substitute y for 0 in the equation and then isolate x. You get to this value. So this is the x-intercept. That means the straight line should cross the x-axis at that precise point. Then find the y-intercept. That is the position over the vertical axis where the line crosses that axis. So you need to substitute x for 0, then you isolate y, and you get this. Y equals -6, meaning this is the y-intercept. So that means there is a unique straight line that contains those 2 points, or that crosses those 2 points, and that line should be obviously the line represented by that equation. Yeah, it's obviously an infinite line, right? So notice what happens when you draw or intend to draw an infinite line. You can't represent the whole thing, just a part of it. But you understand that a straight line over the xy plane actually divides that infinite plane in two halves. One half that is above the line and another half that is below that line. So this is what we call, semi-planes. So actually any straight line drawn on the xy plane divides that virtual plane into semi-planes, right? So, and that's it. Now, once we have the graphical representation, then we can probably do something else. Some questions require that you first find the graphical representation of a line based on its given linear equation. All right? Now, see how the conversion of the equation of the line into what we call the geometry form, shows how, these properties for the constant values m and b work. If we isolate y from the equation above, we get y equals 3/5 times x less 6. So what does 3/5 means? This is the slope of the line. And this is constant value b. Notice how this value matches precisely the vertical position where the line crosses the y-axis. But what about 3/5? Well, basically speaking, this value here is just, the value of a trigonometric function, If this line has an elevation angle alpha regarding the horizontal axis of the plane, then the value of the slope is simply the value of the tangent of such angle. But in the GMAT, we never mess with trigonometry. So it is actually useless to interpret the slope of a line in terms of this precise trigonometric definition, the tangent of the angle. Yeah, instead, you can learn to view the slope, as a number which will indicate two types of information. First of all, with the sign, of the value, this constant value, the sign will indicate whether a line has, an ascending orientation when run over from left to right. That is, if the line looks something like this, or if the line looks something like this. If it has an ascending orientation when you run over the line from left to right, then the sign of the slope should be positive, while if the sign is negative, it means it has the opposite orientation, descending from left to right. You can see clearly that this line has an ascending orientation from left to right, right? So this is practically the value of the slope. But then it has some more value. You know, the precise ranges of values for the slope will determine how steep or how flat the elevation of the line or the declination of the line is. And we'll discuss that just next. Okay, so let's talk about the slope of a line, which we know to be, you know, the tangent of the elevation angle the line forms with a horizontal axis. That's a precise definition. So what does it mean when the slope of the line is 0? Well, if you remember, if this is the equation, imagine that m equals 0. So that means this term is cancelled, and you have an equation like this. This means that we have a horizontal line, okay? A slope 0 means the equation of the line looks like this, and it's basically a line which is totally horizontal. In other words, it's parallel to the horizontal axis. Now, we've already talked about the sign of the slope. A positive sign means ascending from left to right, a negative sign descending from left to right. But what about specific values for the slope? It's interesting what happens when the slope, okay, of the line, you know, is actually 1. You can see 1 means that the line forms an angle of precisely 45 degrees, which means it's entirely symmetrical regarding both the horizontal and the vertical axis, you know. But what happens if you have a slope greater than, let's write it in this way, greater than 1? If the slope is, let's first make this interval. What happens with a slope which is between 0 and 1? A positive decimal, would that have a special meaning? Well, it simply means that the angle of elevation of the line is a soft one, meaning this angle is less than 45 degrees. That's what it means to have a slope with a fractional or decimal value, such as this one, 3/5, right? That's 0.6. That means you can see that the elevation angle is not that steep, okay? It's like a soft elevation, not so abrupt. Yeah, so that comes precisely because the angle of elevation is less than 45 degrees. If the slope is greater than 1, that means that actually the elevation angle is greater than 45, but less than 90 degrees. Why is that? Yeah, because a 90-degree elevation angle would mean that the line is fully vertical, right? And you know, in that case, the tangent of 90 degrees is undefined, so it doesn't exist. So basically, we're saying that when the slope grows greater than 1, you could have 5, 10, 11, 100, etc. That means that the elevation angle goes higher and higher, closing in to 90 degrees, but without ever becoming 90. Because when the actual elevation angle were 90 degrees, you would have a fully vertical line. And at that moment, the equation of the line totally transforms. You no longer have this normal equation, but something like this. This is what you will see in questions where you are given vertical lines. Fully vertical lines simply look like x equal a constant value. Okay? And the same similar reasoning here applies to slopes, that have a negative sign. If the slope is -1, that means that the declination angle the line forms with the horizontal axis is just 45 degrees. But a slope, between -1 and 0, that means that the declination angle is less than 45 degrees. That is, a true negative decimal for a slope means a soft, descent, in the declination of the line. But if you have a slope that is actually more negative than -1 or less than -1, that means that the angle, should be declination angle, descending angle is between 45 and 90 degrees. So that's how it works. Okay? So that's all you need to understand about the slope. You will never be asked to calculate, for example, the slope from the actual value of the declination angle. There are no such questions in the GMAT. Because in the GMAT, you never deal with trigonometry. Okay, so another thing. How do we find the basic parameters of the equation of a line, which we know to be M and B, right? From the coordinates of two given points. If you have, for example, points P and Q, right? Then these points have their corresponding coordinates. You are given the pair of coordinates for P and Q. So you might be able to find, the full equation of this line. So let's see that, how it works. Let's just here imagine 2 points on the straight line. Okay, for example, point P has coordinates -7 and let's say 2. And to keep consistency with this diagram, we'll imagine another point, which is, somehow located, above and to the right position of P. So you have a horizontal coordinate of 13 and a vertical position of like 7. So 2 arbitrary points. So what's the equation of the line that crosses those 2 points? So we can do this, in 2 steps. First, using the coordinates, we'll figure out the slope, the value of this constant m, right, in the equation of the line. How do we do that? Well, this is, a well-known formula that is known as the rise over run, meaning rise, the difference in altitude or in the height of 2 different points, and the run, the horizontal difference between 2 points in position, that is to say. So what's the difference between the vertical positions of the 2 points? For example, we can see here that if we subtract 7 and 2, right? Here, the vertical position of Q and the vertical position of P. Notice that here I'm following this convention. I'm subtracting in this way, Q minus P, right? Or Q less P. So what about the vertical or horizontal difference? Well, let's take 13 and subtract with -7. Let's now continue with the lesson. So if we formulate this ratio, this quotient, we would have, to subtract 7 and 2, which is 5, and then this difference, an algebraic difference, 13 less -7, so that transforms into an actual sum, right? 20, positive 20. So, and what is this? That's simply 1/4. So 1 over 4, 0.25 is the slope of this line containing or crossing these 2 points. So it would look like, y equals 1 over 4 times x plus b. So all it takes now is to define the actual value of b, constant b, in order to have the complete equation. And that, is the second step. You can do that very easily. You reason like this. Points P and Q, which are supposed to belong to the common line that crosses them, they belong to that line. And how do you prove or you assess whether they belong or not? Well, simply by substituting the coordinates of either of the points in the equation of the line, that should yield a true equality. In other words, if I were to substitute 13 and 7 in this equation, the equation should turn out to be true. Let's do that. So 7, substituting y, equals 1/4 multiplied by x, that is the value of 13, plus b. And this equality has to be true. So if this is true, then from this equality, I can easily isolate the value of b, right? Yeah, b would be, 7 take away 13 over 4, which, giving common denominator to this operation, we have this, and finally the value of b. So now the actual equation of the line becomes, okay, this line L that crosses both points equals, or this following equation, y equals 1/4 multiplied by x plus 15 over 4. That's it. That would be the equation of the line that crosses the 2 points, P and Q. So you can do that. Say, for example, if they were to give you not the coordinates of 2 points, but the coordinates of a single point and the value of the slope, is like if you were at this point in the process already. If you know the slope and know the coordinates of a single point in that line, do exactly that, okay? Form the equation like this, substitute the coordinates x and y, and isolate the value of b. That would be it. So let's now consider some other properties. Yeah, something interesting is when you remembered, the theory of linear equations with two variables. So you had a number of situations, right? We analyzed cases, how two linear equations with two variables can be dealt with, as if they actually meant, a consistent system that can be solved in finding a unique value for x and y. Yeah, that's one possibility. Another possibility was when the two equations actually represented the same relationship between the variables. In other words, either of the equations could be transformed into the other. That means that we don't have a unique answer for the values of variables x and y. And there was yet a third case in which the two equations were unsolvable because they actually contradicted each other. And that meant no values for x and y could be found. But these three cases actually have, a geometric interpretation if we consider that any linear equation with two variables represents a straight line on the xy plane. So, for example, one of such cases, the second one, remember when we had two equations where, all the coefficients in those equations were fully proportional? Well, that's precisely what happens when two lines are parallel. When two lines are parallel, their slopes have to be the same, right? The same. So, for example, you have this. Let's write here two sample equations, linear equations with two variables. 2x plus 5y equals -1, and 2x plus 5y equals 4. I apologize. I was referring to the third case we analyzed. When, the equations don't seem to be the same, but actually they can transform one into the other. So you see, you take a look at this and say, oh, these equations are different, but can they be solved together? No. Why not? Because they are contradicting each other. Which one is true? That 2x plus 5y equals -1, or that the same expression equals 4? Just a single expression like that, 2x plus 5y, couldn't be -1 and 4 at the same time. So there are not two numbers in the whole set of real numbers that could satisfy these equations at the same time. But notice what happens when you take these equations into the geometry form. Isolate y in the first. What you get? Oh, you would get this, right? -2 over 5, right? X, and here -1 over 5. Less 1 over 5. So that's what you get, in the first equation. In the second, isolate y and you get -2 over 5 times x plus 4 over 5. So what do they have in common? Clearly, they have in common the same slope. So what does that mean? It means that these two lines having the same slope, but clearly differing in the y-intercept, they don't cross the vertical axis at the same point. So these lines actually never cross. This is the situation of something like this. Take a look. You have an xy plane, and you have a line such as, for example, this. Okay? With a negative slope crossing the y-axis at this point, 4/5, and you have another with the same slope crossing the y-axis at a different position. These lines will never touch each other, right? They are kept always at the same distance. So why algebraically we couldn't find a solution for this system of equations? Simply because finding a solution for a system of equation means finding a common point between two straight lines. If each of the equations in a system of linear equations with two variables represents a straight line, finding a solution for such a system means finding the point where the two lines cross each other. But two parallel lines will never cross. So no wonder that we couldn't find a common point or intersection point. No common point, no solution algebraically, because that's such a point, a crossing point for the two lines doesn't exist. All right? So when you solve a system such as, you believe the system is consistent and you can find a solution, that's simply because on a, xy plane, you are crossing two lines, and this common point is the solution for your system of equation, right? You have an equation whose, or a line whose equation is something like this: ax plus b times y equals c, and you have another, remember our notation, dx plus ey equals f. When you can solve these two equations, is because the lines cross, all right? And there is one special case here that we also want to comment. What happens when two lines on the xy plane, they cross not just like this, but forming a precise right angle, that is forming a 90-degree angle? Well, if they form a 90-degree angle, then the slopes have these behaviors. their product of the slopes of such two lines will always be -1 if they cross perpendicularly. Okay, so for example, imagine you have this line M, whose equation is y equals 2 over 5 times x plus 3. And you have this other line N, whose equation is -5 over 2 times x minus 17. So what can you see about the slopes of these two? If we were to multiply these two numbers, we would obtain exactly -1, meaning that if you graph these two lines on the xy plane, you will notice they cross perpendicularly. Okay, so that's a property perpendicular lines have. In the GMAT, a special notation to represent two lines that are perpendicular. First of all, you need to remember that in the GMAT questions related to coordinate geometry, lines are always labeled with small letters, M, N, whatever, okay? While points are usually labeled with capital letters. So, this means that M is perpendicular to N. The two lines are perpendicular to each other. The symbol such as an inverted T, right? While the symbol with two small lines, vertical small lines together, this means parallelism. That is, M is parallel to N. Okay? Yeah, it's interesting because some questions in the GMAT don't even mention the words perpendicular or parallel. They just use the symbols, particularly in data sufficiency. Okay, here's another interesting property lines have. It's called the property of the perpendicular bisector. First of all, a perpendicular bisector is a name we can give to a line or line segment that does either of two things. For example, it's a line that divides an angle in two equal parts, or it is a line that divides another line segment in two halves, in two equal parts. For example, this line over here crosses the segment AB. You can see how the endpoints of this segment are labeled with two capital letters A and B, right? That's what I was talking about. And the reference to any line segment in the GMAT is like this. Probably you remember your geometry courses. Can you expect to see this one? No, never. In the GMAT, they don't use that notation. They only use this. This means either the line segment AB or it means the length of the line segment. So they might tell you, for example, AB equals 6 or 6 units, whatever, meaning that the distance between points A and B are 6 linear units, or that the length of the segment is 6 linear or length units. Okay, so this notation can mean both. Can mean the segment as an object, a geometric object, or it can mean the length of the segment or the distance between its two endpoints. So take a look. If a line crosses a line segment precisely by its midpoint, and it crosses the line segment forming a right angle that is a 90-degree angle, so you say that this line is the perpendicular bisector of that line segment. Okay, that's a property. No, this is not a property. Which property is here? No, it's simply a definition. But here is the property. Take a look. Using another color. Say, for example, that you define any point over this perpendicular bisector. Let's talk about point Q. So, if you were to measure the distance between point Q and the two endpoints of the line segment being intersected by this bisector, so those two distances always have to be the same. Oh, that's so basic, you would say, right? Yeah, it goes without saying. Yeah, out of symmetry, you could get yourself to that conclusion on your own. the distance between any point on a perpendicular bisector to a line segment is always the same to the endpoints of the line segment. It goes without saying. It would have to be the same about point P over here. This distance and these distances, let's call D1 and D1, have to be the same as well. Okay, that's it. Let's now talk about some, okay, here let's omit this for a moment. Let's see some examples, okay? Let's take a look at question 1. Well, the question, as you see, is formatted as a data sufficiency question. Yeah, I will not write the options because you know better. And the question goes like this. Notice some common characteristic to any coordinate geometry question in the GMAT. They begin with a formula such as in the XY plane, in the rectangular coordinate system, etc. Okay? Always like that. So the question goes, is the slope of some line L positive? And you have these two statements. So what's the answer, do you think? Remember, the slope of line L positive. Imagine you have a line L such that, you know, the equation of the line is like y equals m times x plus b, right? M the slope, b the y-intercept. And so they're asking you whether the slope is positive. That means that the question is this: is m greater than 0? That's the actual question, right? So what do you think? This is not rocket science, so we'll just leave stand by for a minute, okay? Think about it. First says the x-intercept of L is positive. Second says the y-intercept of L is positive. What does that mean in each case? Let's go over this together.
Quadrant.
The first one is sufficient? Yes or no? It's not much to think. It's either sufficient or insufficient. What are your arguments, people? Can you visualize for a moment a line having an x-intercept with a positive sign? People, what does the x-intercept mean?
It's not enough.
Not enough. Why? Why?
Because you just have one intercept. It could be any angle. If you take the first one or the second one, it's not enough. You've got to use both.
Yeah, people, thank you, Lorena. The x-intercept is, you know, the position where the line crosses the x-axis. If the x-intercept is positive, they are essentially telling you something like this. The line crosses the x-axis over a point in this position, the right hand, you know, side of the horizontal axis. It doesn't cross over here. It crosses only in this position. But does that tell you the orientation of the line? So, for example, you could have this line or you could have this line. Clearly, the information of the sign of the x-intercept alone doesn't tell you the slope of the line, let alone the sign of the slope. You don't know. This could be, for example, here is a negative slope or a positive one, and here you would have a negative slope. Both lines crossing with an x-intercept of positive sign. So clearly this is not sufficient. You can't answer the question. You have two possible answers, so not sufficient. Second statement, the y-intercept of L is positive. So this is a similar analysis. Now they're telling you that this line crosses the y-axis over here, you know, in any part of the positive half of that axis, that is above the origin. Here's the origin. But having a line crossing in that position, does that tell you the orientation of the line? Clearly it doesn't. You could have infinite lines, each of a different orientation, so you can tell whether the slope is positive or negative. Not sufficient either. And now you are compelled to analyze the two statements together, the two conditions being true at the same time. So notice what will happen. The first tells you that the line crosses in any point in this part of the x-axis, let's say something like this, and the second one is telling you that the line crosses in this half of the vertical axis, let's say a point like this. But if you just pick a point in the upper half of the vertical axis and the rightmost half of the horizontal axis, you will have a slope or a line with what kind of orientation? It will always be declining or descending from left to right. That's equivalent to a negative slope. It couldn't be otherwise. Yeah, you can change, right? The position of both intercepts. Let's try that. For example, what about this? Or what about this? It doesn't matter how you move the points. The orientation will always be descending from left to right. So this is a unique answer. The answer to the question is a no. If you take the two statements together, the orientation of the line is not positive, but negative. But it's a unique answer, so sufficient. Correct answer, option C. An interesting variation of data sufficiency, coordinate geometry, is considered a blend of geometry and visualization, right? And probably that's why, they kept this question format in the GMAT. Yeah, you have to be very analytical to nail the correct choice. Let's see another example. Let's try this question. Line K lies in the XY plane. What is the y-intercept of line K? Notice they're asking you about the value of the y-intercept because the y-intercept is a number, right? A real number. You have these two statements. Yep, please. Take your time. All right, so what do you think? Any opinions? We know that if we have a line, okay, the line must be represented by some linear equation with two variables. So let's write generically y equals mx plus b, where m and b are the constants we already know. So what's the y-intercept of line K? They're asking you about the value of b, the constant b. So what can we do with statement 1? Notice they are telling you the slope of line K is 3/2 times the y-intercept. What does it mean algebraically? What is this? Well, that is constant m, right? And if this is 3/2 times the y-intercept, that means that m equals 3/2 multiplied by b. Can you tell the value of b looking at this equality? No, unless you know the value of m. But do you know the value of m? You don't. So since m is completely unknown, then the value of b is therefore equally unknown. This is not sufficient. You could have anything for the value of b. All right, so let's go to statement 2. The x-intercept of line K is -2/3. You remember what we said, how you obtain the x-intercept of any line based on the linear equation that defines it? Well, you may remember all it takes is substitute variable y for 0 and then isolate x. If you do that, the value of the x-intercept becomes -b/m. That's what you get. Or if you already remember this formula, good for you. So they are telling you that the x-intercept, that is to say this expression, equals -2/3. Interesting. This is the same as saying b/m equals 2/3, or the same as saying m over B equals 3 over 2, or the same as same M equals 3 over 2 times B, which is pretty much the same relationship they gave you in statement 1. We know this is not sufficient. Trying and combine these two statements together would be the same as trying to solve a system of equations that are equal to each other. You get nothing from that. There are infinitely, possible solutions. So the conclusion is both M and B are fully undefined with these two statements, even if you take them together. So the correct answer choice is E. That's it. Questions? Doubts? No? Okay. Actually, this question is, something you can approach using just algebra, the algebra of linear equations. Let's see another example here. In the xy coordinate plane, a different beginning formula. Is point P equidistant from points, these 2 points? Is point P equidistant? That is the distance between P and this point the same as the distance between P and this point? That's the meaning, right? And they tell you in one statement the vertical coordinate of point P, and in the second the horizontal coordinate of point P. Here, this is an interesting question because just from finishing reading the question, one person, who considers themselves very logical would say, oh, but just one coordinate won't help me establish the true distance between a point and another. So if I take the two statements together, now I have the exact position of point P. Therefore, I can establish whether the distance between that point P and the given points in the question is actually the same or not. No matter what that distance will be, I always have a definitive answer from taking the two statements together. So the correct answer must be C. But is that the case? Take your time to analyze this one. Okay, people. What are they? What they're actually, giving here is not just any 2 points. Well, these 2 points have something in common. And what is common to the points is the same vertical position. So if they are at the same vertical position, they could be placed over same horizontal line, right? Here is 3, -5, and somewhere over here should be the other point. But they are on the same vertical or horizontal line because they have the same vertical position. So to know whether a point is equidistant or has the same distance to these 2 points, do we really need the full position of the point? If we were to know the vertical position of this point, well, the vertical position actually indicates a full horizontal line as all the possible locations for a point with a given vertical position. And curiously, the first statement simply tells us that the point P is at the same vertical position as these 2 points. In other words, the point P could be virtually any possible point on this horizontal line that contains. Clearly, there is just one position over that horizontal line that would be fully equidistant at the same distance from both points, while all other positions wouldn't be equidistant from those points. So clearly, with this unique position, we would have a yes for an answer, while for any other, we would have a no. clearly this statement is not sufficient. Why? Because we simply don't know what is the horizontal position of the point. The x coordinate is unknown. So because of that, this is not sufficient. Now think about statement 2. Statement 2 says that the x-coordinate horizontal position of point P is -1. Now think about these 2 points on the same vertical position. Imagine a point like this. Okay, imagine a point like this. Imagine P is over here. With that position, you clearly can tell whether the point is equidistant or no. Under all appearances, the point seems closer to the point in the leftmost position, -5, -5, and seems farther from the other one. Yeah, that's because here you can see the true position of the point. But what would it be like to just know the x-coordinate of a point? It just means that you know the point is located over, one vertical line. And on that vertical line, the position of the point could be anything, because all those points on the same vertical line would have the same horizontal position. People, would that be enough? For example, if you just know what is the precise location of this virtual vertical line regarding the points we are measuring. Okay, or sorry, not this, but the ones in red. These two. If we were to know that the point P is on a given vertical line whose horizontal position is clearly known, would you be able to tell whether the point is equidistant? Yes, you could find the answer to the question. For example, say that this were, let's use another color, this were the vertical line containing point P. Okay, any point on that line, if the line is not equidistant from the 2 points we are measuring, obviously this point will not be equidistant. There is only one possibility that the point on a vertical line, on any position on a vertical line, would be equidistant from these 2 points. And what would that condition be? Well, if you consider that these 2 points are forming a horizontal line segment, there must exist a single line which crosses exactly through its midpoint. And any point, that's called a line bisector, right? A perpendicular line bisector for the segment with endpoints given in the question. So, if a point belongs to that perpendicular bisector, no matter in which vertical position is found, it will always have the same distance to the 2 points. But if the point is located anywhere else that is on a line that is not the perpendicular bisector, you also have the possibility to answer the question. The answer would be on the negative. If the point is located on the perpendicular bisector, there is a yes. If the point is not located on that perpendicular bisector, the answer is a no. So you have a definitive answer. Since you know the horizontal position of that vertical line, then you can tell yes or no. Now think about this. Is this horizontal position at the same distance from this and this? Well, it happens to be the case. Take a look. You have 3 here, you have -5 here, and you have a line crossing at point -1. What's the distance between these 2 points? 4 units. The distance between these 2 points, 4 units. So it just happens that point P is located, in a horizontal position such that it coincides with a perpendicular bisector of the line segment whose endpoints are the points in the question. Therefore, any point placed on that perpendicular bisector must be at the same distance from the endpoints of the line segment being crossed. In other words, the answer with statement 2 is a yes. And therefore, the correct answer to the question is option B. Okay, so that's how the property of the perpendicular bisector works in this kind of question. Now, let's see some more theory before going on. In the GMAT, sometimes we have to deal with questions that use linear inequalities with two variables. What are linear inequalities with two variables? Expressions such as this, you can see. They look a lot like, linear equations, but they may adopt this form. Like, for example, or perhaps it's also possible to see greater than or equal, or the other way around. That is to say the other inequality symbols. Maybe, yeah, any of the four represent a linear inequality with two variables. If a linear equation with two variables represents a straight line on the plane, what does a linear variable inequality represent? Well, essentially an area. What kind of area? Remember we said when you draw a straight line on a plane, you have to realize that when you draw a line such as this, it's not really just the line is ended here or here. This is an infinite line. So it can be represented beyond the limits of the screen, right? Yes, but you guess that, you understand that. So the infinite straight line being drawn on a plane actually divides the plane in two halves, two infinite semi-planes, one above and the other below the line. Can you visualize a semi-plane? An infinite region delimited on just one place by an infinite straight line, while to the other direction it opens endlessly. Yeah, that's what a semiplane is. So, one of the two semiplanes that form on either side of a straight line, that could be the actual, set of points, because it's an infinite set of points, that would comply with one linear inequality with two variables, such as this one. Only it remains to be defined whether the inequality we are facing represents the upper semiplane or the lower semiplane. That is, the semiplane above or below the line. So how do we do that? Well, first, when we need to represent or define graphically what's the area that a certain linear inequality represents, we always start with the corresponding equation. So forget for a moment about the inequality symbol and replace it for the equality symbol. Work with the equation. Use the concept we saw to draw, the corresponding straight line on the plane, on the XY plane. So what was the method we saw? It's defining graphically the X and Y intercepts and then connecting those two reference points with a line segment. So let's do that. If we take X to be 0, then what is the value of the Y intercept? The Y intercept would be 4, positive 4. And if Y were 0 here, then the value of the x-intercept would be negative 3. So you can see if you draw those 2 points on straight line, here is 4, our y-intercept, and here is negative 3. That means the line you see there is actually the representation of this equation, right? Yes. Now, we know that there are 2 semiplanes, one above and below that line. So how do we define which one corresponds? Well, here you have a very simple and graphical method. Choose any point on the plane whose coordinates you can tell clearly. Usually, such point, the easiest point you could think of is the origin itself. Yeah, you can see the origin here. Not only you know that the coordinates of these points are the simplest possible, but you also know what is the relative position of such point regarding the line you just drew on the plane. You can see clearly from this diagram that the origin remains below the line or in the semi-plane that is below the line. Why is that relevant? Well, think about it. Do you remember what measure we used to assess whether a point belonged to a certain line or not? We substituted the coordinates of the point in the equation of the line to see if the equation became a true equality. If it would, then you knew that the point belonged to that line. Similarly, we know that a certain point, a designated point over the plane, belongs to a given semiplane if substituting the coordinates of the point in the inequality that represents the semiplane, the inequality turns out to be true. So, can we tell whether this point 0, 0 is or is not a part of the area represented by this inequality? Let's make a test. Let's substitute the coordinates of this point in the inequality. 4 times 0 less 3 times 0 is less than negative 12. So essentially this is 0. 0 is less than negative 12. Oh, this is false, right? Why is that? Well, that means that the point, the origin of coordinates, doesn't belong to the semiplane represented by this inequality. In other words, in practical terms, it means that the semiplane we're looking for is actually the semiplane above the line, because that semiplane by no means contains the origin. So that's why the origin cannot satisfy the inequality, because this is the semiplane that such inequality represents. Not just the triangle, people, okay? The semiplane is infinite. Yeah, you can visualize with a shaded area. It extends endlessly, okay? Upwards and leftwards. So that's how you work with linear inequalities. On the other hand, what would have happened if when substituting the coordinates of the origin, the inequality turned out to be true? Well, then that means that the origin itself is a point that belongs to the area we're looking for. Since it belongs to the area below the line, that means the semiplane we're looking for, or the semiplane that is represented by that inequality, is the one below the line. That would be the interpretation. Okay, so that's it. That's how you work with two variable inequalities. Now, this is, seldom. I've probably seen just 2 or 3 questions in my whole life related to, other figures and regions. Remember the general equation? We talked about this when we discussed inequalities. The general quadratic equation with 2 variables. But actually, the quadratic reference here is just about variable x, right? Because the variable y doesn't have an exponent 2. So what does this 2 variable equation represent? It represents the curve parabola. We're familiar with that curve. So what would an inequality where the equality symbol is substituted for less than or greater than means? If the equation represents the curve parabola, this equation or quadratic inequality with 2 variables actually represents the area above the parabola, whenever the parabola has its 2 branches oriented upwards. Remember, that happens, when the coefficient, so in this drawing, the coefficient A is positive, okay? That means a parabola with its two branches oriented upwards. When it is the other way around, that is a parabola orientated, downwards with the branches, that means the coefficient of the quadratic term is negative, right? So that's the interpretation of this region. And this quadratic inequality means all the region below the parabola. Okay, so that's it. Um, well, let's continue with the remaining examples. Let's try this one. In the xy plane, if line k has a negative slope and passes through the point negative 3, s, is the x-intercept of line k positive? We have two statements, right? The slope of line k is negative 3, s is less than 0. So actually two interesting approaches. One totally algebraic without having to visualize anything, and one almost entirely geometrical, which requires visualization. So think about it. You have a line with a negative slope. So what is a line on the plane represented with? A linear equation with two variables of the form y equals mx plus b. Telling you that line k has a negative slope means that m is a negative number. And the fact that the line passes through the point means that if you substitute these two coordinates in the original equation of the line, it turns out to be a true equality. So let's do that. You substitute y for s, you have s equals m times x, that is negative 3 times m, plus b. B, not 6, people. So you know that this equality is a true one because of that definition, that that point belongs to the line. And the question is the x-intercept of line k positive? Now, if you've taken, the definition of the intercept seriously, you must remember by now that this is a single formula. This negative b over m, that is the value of the horizontal intercept. The question is whether this is positive, which would be pretty much the same as asking whether b over m is negative, right? So this is the question. B over m negative. Do you remember what happened when you have this kind of inequality hanging around? That a or x over y is less than 0. What does it mean? Remember? What does it mean about the signs of the two quantities? It's basically they're asking you, are b and m of different signs? Because that's what the inequality means. That b over m is less than 0 if they are both real numbers, means that the two numbers have opposite signs, right? So are b and m of different or opposite signs? That's the true question you need to reply to. So let's go, on this question using a purely algebraic approach. You know that the slope of line k is negative 3. So is that of any use? The slope of line k is negative 3. So what is the slope? M. I know that the slope is less than 0. Now they are telling me that it's exactly negative 3. People, with this information, is there any way, any possibility that I could know the value of B? Any? How could I connect M with B? Here there is an interesting relationship, right? S equals negative 3M plus B. So it's an expression that connects M and B. Unfortunately, this depends only on S. Sorry, also on S. That is to say, if from that relationship I would like to establish the value of N, I would first have to know what the value of M is and the value of S is. Unfortunately, S is unknown. I have nothing to say about S. Here, a default assumption is that S is just a real number. That's not enough. With that, I can't establish what the value of B is, let alone the sign. Okay? I don't know the sign. So statement 1 is not sufficient. I don't have sufficient information to tell whether B and M have different signs. What about statement 2? S is less than 0. Oh, this is interesting. Let's take into account just the information above, please. Not statement 1, only this. This is what we know to be certain from the information prior to the question. So I know that S is less than 0. But if this is true, then this expression here, which is equivalent to S, must be negative. If negative 3M plus B is negative, what does it mean about B and M? Notice that this means that B is less than 3M, properties of inequalities. People, can I establish or form the ratio B over M? Yeah, I could do that, right? If I just divided both sides of the inequality by M, the common factor. You divide here by M, I divide here by M, and then I form the ratio which relates to the question. But be careful, what is the sign of N? Do we know? Yeah, we know it's negative. So when you divide by a negative number, remember what needs to happen. B over M would be greater than 3. B over M greater than 3. Right? This has to change because we are dividing by a negative number, a negative factor. So B over M being greater than 3 means that this is positive. Therefore, the answer to the question is a no. B and M have the same sign. They don't have different signs. So we have a unique answer to the question. Correct choice, B. Notice that this, approach simply uses whatever we learned about inequalities, right? Remember that first property of inequalities we discussed? Well, now it's important, right? So this is it. What would be more geometric approach that would require that you try and visualize what the problem describes? So let's see if we can figure this out. Let's take a look at what the first statement means geometrically speaking. If you have like this XY plane, okay, X and Y, and they tell you that the slope of line K is negative 3, and at the same time they are telling you that the point passes through this point. Notice, negative 3, S means that the intersection point must be located, on a vertical line that passes through this position. Any point on that vertical line would have a horizontal coordinate of negative 3. Unfortunately, we don't know S, so S could be anywhere along that vertical line. Now, let's start imagining what would the line K would be what line K would be like if it crossed, through the point -3, comma S, considering very different values for S. Let's say, for example, that S were a very big positive number. So it were something like here. So if you were to draw a line with a negative slope of -3, that means, since it's less than -1, that the declination angle must be greater than 45 degrees. So it's a steep line with descending orientation. Perhaps something like this? Something like this. So what is the x-intercept? Well, it's positive. And if S were very big, or very, very far upwards with a very big positive value for S, then probably the line could look something like this, right? With an x-intercept that would be clearly positive. But now let's imagine the opposite situation. What would happen if S were a negative value? Nothing forbids that possibility. So we are compelled to consider that. If S were negative, imagine, S being over here. So the intersection point, or that crossing point, would be in the third quadrant. And a point or a line crossing the third quadrant with a negative slope of -3 would look pretty much like this. Now we see that totally, opposite from the first two cases, the x-intercept would not only be negative, but would be to the left of -3. It would be more negative than -3. So now we clearly see that here we have two answers to the question. The x-intercept could perfectly be both positive or negative. So that is why this is not sufficient. Here, these cases represent a yes for an answer to the question. This one represents a no, right? So we've visualized what the first statement means, geometrically speaking. What about the second? Can we truly visualize the second statement? Well, the second statement simply says S is less than 0, meaning that the point where this line K crosses, is a point located in the third quadrant. Now let's try and visualize the third quadrant like this. Here's the y-axis, the x-axis, the origin. We know that the crossing point for this line has these coordinates, -3 and S. And if S is negative, that means that the point could be on the vertical line that passes through this position -3 and any possible vertical negative position. So, for example, this one. Make a line cross that point with a steep negative slope. So it would look like this. Right? A negative slope would always determine an x-intercept that will always be, now here we don't know really how negative is the slope. Remember, we don't need to look at the statement 1. Statement 1 said that the negative slope was -3, but with information of statement 2 alone, we don't really know how negative K could be. So let's consider different degrees of negativity. All right? Imagine a very negative value of K. Let's imagine a not so negative value of K, a softer, but crossing through the same point. So it means when the slope becomes softer, less negative, what happens is simply that the negative the x-intercept of the line goes further and further to the left of -3. So no matter how you change, even if you make the slope a very, very negative, something like, for example, this, very, very vertical. Even in that case, the x-intercept will always have to be to the left of -3. In other words, with these different cases, we can visualize that the x-intercept has to be less than negative 3. So this confirms that the x-intercept will never be positive. The answer to the question is a no, and therefore we have sufficiency with the statement 2 alone. Which way do you like most? Which way do you like better? Just purely algebraic or more geometrically oriented? Truth is, people, if you practice this kind of question and get, a faster sense of what is going on in geometry terms, then you could actually be solving these questions faster and faster than taking just the purely algebraic approach. Yeah, algebra is useful, but if you can get to visualize cases like this, then obviously you will be performing faster. Okay, let's see another example, unless there are any questions, doubts, or something. Speak up. Now is the time. All right, let's then turn to question 5. In the xy plane, lines P and Q intersect at point 0, 5. Is the slope of line Q negative? And you have those two statements. Yep. Some time to try this one. Okay, so what's the answer, do you think?
Both together are sufficient.
Okay. Who said that?
Me, Gabriel.
Okay, thank you, Gabriel. Thank you. Okay, so anyone in agreement with Gabriel? Anyone contesting that answer? Actually, Gabriel is accurate, people. You take the two statements together, that yields a unique answer to this question. What kind of answer it is, Gabriel? Affirmative or negative?
It is affirmative. The slope of Q, it's negative.
All right, thank you, Gabriel. Then, that confirms you're right in your analysis. People, if the x-intercept of a line is negative, that tells you nothing, as we saw the first question, right? That couldn't tell you anything about the orientation of a line. But you have now another reference. This, that two lines cross at this point, 0,5. That means here, right? This point, in this position, exactly over the vertical axis. So if two lines cross at that point, and you know that the x-intercept of line P is negative, that means the line must go something like this, because the x-intercept will be negative. So this is P, but is this, sufficient? The slope of line, P is well established from this question. Unfortunately, you know nothing about line Q, but only the fact that this line crosses through the point indicated there. So it could be, for example, a line similar to P, that is with negative slope, or in this case a positive slope. It could be like this, it could be like this, yeah, it could be anything. So this is not sufficient. When you analyze the second statement, which says the product of the slopes is -1, well, you know already that the lines must cross in this position, in this point. But two lines crossing there and having a product of slopes -1 means simply that the two lines are perpendicular, right? So it'd be something like this, perhaps. Thing is, yeah, you see clearly from this that it's very likely that while one of the lines has a positive slope, the other has precisely a negative slope, the opposite. The one question here remains: which one would be P and which one would be Q? You can tell simply from watching this diagram. So Q could be the one with a positive slope or the one with a negative slope. You can tell. Not sufficient. Finally, you have to combine the two statements. You have your coordinate system, you have the crossing point, and you have the information that the x-intercept of line P is negative, meaning P is something like this. But if the second statement is true at the same time, then the other line must be perpendicular to P, making that line Q, which clearly would have, negative slope. Notice the orientation, descending from left to right. So the answer to the question is affirmative and it's unique. So the correct choice is option C. Okay, let's try our next. Okay, the question shows a rectangular coordinate system, and the question goes, which quadrant, if any, contains no point that satisfies the inequality you see here? All right, so that calls for the theory we saw a moment ago, right? How to interpret linear inequalities with two variables. Remember, such inequalities represent semiplanes, either of the two semiplanes forming above or below, a line on the plane. So you can try. So which one? All right. Option 4 or quadrant 4? Yeah, interesting answer, Lorena. It could be interpreted. Quadrant 4. Okay, that's a different answer, not Lorena's. Angelo, thank you. Yeah, but actually, if you meant this for an answer, this is it. Okay? Why? Well, let's go over the steps in the procedure we discussed to deal with linear inequalities with two variables. First, let's focus on this, understanding how this line may be represented, on the xy plane. So the method we have is define graphically the position of the intercepts, that is the points where the line crosses the two axes, right? For the y-intercept, you make x0, so that means y would be precisely positive 3, and when y is made 0, then x would be negative 5. Meaning, you have something like this, okay? If the y-intercept is 3, it means the line crosses, over here. And if the x-intercept is negative 5, it means maybe somewhere near this position. So that means that the line crossing those 2 points will be something like this. So now it's just a matter of defining which of the two semiplanes we are talking about. The one above or the one below. Let's try the next step in the method. This point is clearly the origin below the line, right? So substitute these coordinates in the inequality. 3 times 0 makes 0. Less 5 times 0, that makes 0. So you have this. Is this true? No, this is false. Because 0 can be less than or equal than any negative number. 0 will always be greater than any negative number. Being the inequality false, when you substitute x and y for 0, that means that the point we're talking about, okay, doesn't make part of the region represented by the inequality, which means then that the region must be the upper one, the upper semiplane, because that semiplane doesn't touch the origin. And that's why this resulted, right? So now that we see here, we interpret the question, which quadrant doesn't contain any points that satisfy this inequality? You see the first quadrant contains point if the semiplane, shaded, right? The second as well. The third also contains point in that semiplane. The only one quadrant that doesn't touch the semiplane at all is the fourth. That's why. Okay? Let's continue. Another example. So let's try this. This question is interesting because, no matter how you try to visualize it, it will be very difficult to visualize. So we'll have to resort to algebra to deal with it. Question is P, Q, yeah, couple of coordinates, right? A point in the line y equals to x plus 3. Yeah, this is like a very normal expression to represent a line, linear equation with two variables. And you have two statements. The first one is this expression, a product of two expressions involving P and Q equals 0. And the second is similar, right? Yeah, with a few differences. And that's it. How could we approach this question? Just a minute to think it over. Something we can say about this question is that there are no patterns here to actually try and visualize this geometrically. Well, just one thing, right? If a point belongs to a line, then it must satisfy the equation of the line. If P, Q represents a point in the line with the equation indicated, then substituting the coordinates of that point into that equation should yield a true equality. In other words, if you were to substitute y for q and x for p, you would obtain this, right? Okay. So q equals 2p plus 3. If this were true, the answer to the question were affirmative, then this equality should be true. In other words, the original question is equivalent to asking, is q equal to 2p plus 3? But then, just being a bit observant, the expression in the first factor of statement 1 and the second factor in statement 2 looks a lot like this. Why? Because if you place q on the right side of the equality, this becomes, this is equivalent to asking whether 2p take away q plus 3 equals 0. That is the true question. Notice, this is precisely the expression appearing here and here. So, is that expression equal to 0? Can you tell from statement 1? So, we'll deal now as if this were the true question. Actually, it's equivalent to the original question. Determining whether that expression, 2p less q plus 3 equals 0, is the same as giving an affirmative answer to the original question. And vice versa. you know? So, what about statement one? You have, a basic structure that looks like this: x times y equals 0. Yeah, you can analyze from this basically that either of the two factors may be 0, but do you know which? All we can tell about statement 1 is that it means that 2p minus q plus 3 equals 0, or 3p plus q minus 5 equals 0. If this were a possibility, actually it is a possibility, if this is true, then this means an affirmative answer to the question. But what happens if this is true? If this is true, the second possibility, is it necessarily true that 2p minus q plus 3 equals 0? No, because that would be the same as saying, pick two values for p and q that make this true. And then, would those arbitrary values would necessarily make this, true? No, unless you solve this kind of equation system. If you solve this system, you would find the two values for P and Q, which make not only this true, but also this true. But what about any other values of P of Q and Q that do not concur with the solution to this system? Just two values that would make the first equation true. In those cases, you would get a no for an answer to this question. So the first statement is clearly insufficient. What about the second? Well, it's the same thing, right? Now you see that this expression appears as the second factor. So this means that either 3p plus q minus 7 equals 0, or 2p minus q plus 3 equals 0. If this were true, then we know that this means an affirmative answer to the question. But here, this one being true doesn't mean necessarily that p and q will make this question true, or this equality in the question true. Because you can pick the values of P and Q that precisely make this 0 and this 0. Notice it's an or you could pick just two values, P and Q, that make this 0, but don't make this equal to 0. So in that case, that this is true means that you can have yes or no for an answer. Same as in this case. Yes or no, it's possible considering the second possibility. So that's why the second statement is not sufficient. So we are forced or compelled to analyze the two together. Any questions? Any doubts? Gabriel, did you see why B, or the second choice, is not sufficient? Or you have still doubts?
No, I already solved it. Both together are sufficient.
All right. Yeah, thank you. So, take a look what happens, people, when you take the two statements to be together. Together true. Well, basically, it means that 2p minus q plus 3 could be 0, or 3p plus q minus 5 could be 0, or 3p plus q minus 7 could be 0, or the other factor, which is the same, 2p minus q plus 3 could be 0. How do we analyze this? Let's simplify the whole thing like this. You have this, xy equals 0 and xz equals 0. People, can you tell me from these two equalities being true at the same time whether x is 0 or not? Can you tell? Who wants to argue on this? If x and y equals 0 and x times c equals 0, Gabriel, please.
Well, in that particular example, it would be not that clear if x is 0, because j and z could be 0 independently. They could be the same variable, but just two different names for it. But in the
No.
example,
We are talking about three variables, not the same variable. But okay, I understand your point. If y and z were 0 at the same time, that would release x from being necessarily 0. For example, if y were 0 and z were 0 together, then x could be anything. So that means that x doesn't have to be 0. Just from this, you don't know whether x is 0 or not. But let me add one more condition. So if to these two equalities, I add this one. Can you tell whether x has to be 0 or not?
In that case, yes, x has to be 0.
X has to be 0, because imagine the situation where y would be 0, which is a possibility, right? If y were 0, since z has to be different from y, then z cannot be 0. That would make compelling for x to be 0 if this equality has to be true. You know, the other way around. Imagine that z were 0. Well, that would make this equality true. But since y has to be different from z, y cannot be 0. If y is different from 0, the only way for this to be true is that x is 0. So the idea is that this condition compels, that x be 0. This is similar to the analysis of statements 1 and 2. Imagine x being 2p minus q plus 3, and y and z the other two expressions, 3p plus q minus 5, 3p plus q minus 7. We know from the particular shape of these expressions that these expressions, the expressions other than 2p minus q plus 3, they have to be different. Why is that? Well, notice they have a common part and then a different term. No matter which values of p and q you may pick, these two expressions will never have the same value, because 3p plus q is the same number, right? It's a number like n. So n minus 5 is never the same as n minus 7. These two expressions will always be different, same as here. Since they always have to be different, no matter if one of them is 0, since the other has to be different, then that makes compelling that the other factor, that is the like of x, 2p minus q plus 3, it has to be 0. It has to be 0 for the two equalities in the statements to hold true. All right? So that's the point. You can pick, whatever values for p and q that make 2p minus q plus 3 equal to 0. There are infinite pairs, of course. Yeah, but what happens when you pick a pair of values that just makes 3p plus q minus 5 equal to 0? Well, that pair of values could or could not make 2p minus q plus 3 equal to 0, right? But if you have a pair of values that makes p plus q minus 5 0, you are sure that 3p plus q minus 7 cannot be 0. That forces that the other value or the other factor has to be 0. So necessarily, the possible values for p and q, considering the two statements together, have to be two values that make 2p minus q plus 3 0, or two values that make 3p plus q minus 5 0, and at the same time 2p minus q plus 3 0, or two values that make 3p plus q minus 7 equal to 0, and at the same time 2p minus q plus 3 equal to 0. Those are the only possibilities. So in all cases, considering this, the expression here has to be 0. Therefore, C is the correct choice. This looks nothing like a geometry question except for the interpretation of the question itself. But once we interpret this as an algebraic question, the analysis is fully algebraic. All right? Now, let's see our last example for this topic. Question 8 says, in the xy coordinate system, if a, b and a plus 5, b plus 2k are 2 points on the line defined by the equation there, then k equals, and you need to find the value of k. So let's see. You can try. So how do we calculate this? Actually, you have, like different possibilities. Um, did you did you people use the approach that in order to calculate, the slope of a line whose, you know, like for example, sample points. Let's say that you have 2 points that are crossed by a common line and you are given the coordinates. Remember what we did? The slope or the value of m is the difference of y coordinate divided by the difference of x coordinates of the 2 points. So one way could be this, right? You could say, okay, the slope equals the difference of y coordinates, which is b plus 2k, take away b, and the difference of x coordinates would be a plus 5, take away a. So notice what happens, something interesting. You are left with the expression 2k over 5. But at the same time, you already have the equation of the line. All you have to do is simply change the equation so that you can isolate y. Okay? If you isolate y, you get 5y equals 2x plus 9, and then dividing by 5, you get 2 over 5x plus 9 over 5. Clearly, the slope is this coefficient, so this is the same. And from this, you see clearly that k equals 1, right? Oh, this desk is unstable. Well, that's it. So this is one way. There are possibly other ways. Did you do this or did you follow a different approach? What was that? Well, people, you could try, for example, a totally different approach. Like saying, starting from the principle, how do you know a point belongs to a line? If that point satisfies the equation of the line with its coordinates, right? So if I substitute a and b, in the equation of the line, you should get 2a equals 5b minus 9. This equality must be true. Same goes for the coordinates of the second point. So if you substitute a plus 5 where x appears, 2a plus 5 must equal 5 times b plus 2k minus 9. This is also a true equality because these 2 points are supposed to belong to the line. So what happens if we modify this a little bit? Expanding the parentheses, you have 2a plus 10. You have here 5b plus 10k less 9. Do you notice something? What if we subtract equation 1, this equality, multiplied by negative 1 and add with the equality here? So you would have 2a plus 10 minus 2a equals 5b plus 10k minus 9 minus 5b plus 9. So notice what happens. Away, 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 and then 10 equals 10k. Therefore, k equals 1. So that's another way. So it's not like, all the solutions are kind of rigid. Yeah, if you combine different properties, you may get, different ways to the same, different paths to the same solution, right? The important thing is that you try and think of the properties involved. So using different methods, you can still get the same answer. All right, so that's what we can say about coordinate geometry. Lorena, you have a question or comment?
Yes, sorry, Professor. I missed the last step where you eliminated the two A's.
Yeah, because let's say I have this equation, I call it 2, because this is a true equality that,
Yeah.
turns out from the substitution of the coordinates of this point in the equation of the line. It must be a true equality. Same I did for this point. This is the equality we call number one. So
Yes.
here I'm doing this. I'm subtracting 2 minus 1.
Oh, okay.
Yeah, we can subtract equations. Remember, that's one method, for example, for elimination. I'm applying elimination here in order to get rid of the A's, B's, which we don't know, their values, and just be left alone with K, which is what I want to find out. Okay, so that was it. Well, this is all the geometry you may expect to see in the test. It's not like very encouraging because it may be a little difficult to visualize at first, different situations, different cases, but all it takes, as I always say, is practice, right? So practice material is now open for you to, try coordinate geometry questions both in the quantitative and data sufficiency formats so that you can improve on this topic.